Okay, so in the last couple of classes, we saw three different prefix-free codes, all of them being close to optimal. So we first saw the Shannon code, where you assign a code word length of log 1 over p of x to a symbol x, and then the code words themselves are constructed using the binary tree, using the achievability part of Craft's inequality, and that gives you an expected code word length of which is between h of x and h of x plus 1 bits. We saw two other codes, the Shannon-Fano-Elias code, where the code words are constructed by looking at the modified CDF f bar of x, and the code word length for each symbol is ceil of log p of x plus 1 bits. And the code words themselves are obtained by looking at the binary representation of f bar of x and then truncating it to k of x bits. And the Shannon-Fano-Elias code achieves an expected length which is between h of x and h of x plus 2 bits. So it's slightly worse than the Shannon code. We've also seen the Huffman code, where the code is constructed in a recursive fashion. You look at every stage, you merge two symbols with the least probabilities, and then to form a super symbol, and then you keep proceeding till you can't proceed any longer. And this gives you a binary tree. So you start with the two least probable symbols, you merge them to form a super symbol, and then you merge the two least probability symbols to give another super symbol, and then you merge two more symbols to give another super symbol, and so on. Right? So this ultimately gives you a binary tree, and this is what we call the Huffman code. Today we'll see that the Huffman code is optimal in the sense that among all possible prefix-free codes for a given distribution, this achieves the minimum expected length. So given any code, so if I define, say, L star of Px to be the minimum over all possible prefix-free codes of the expected code word length. If I call this L star of Px, then the Huffman code actually achieves L star of Px. So combining it with this particular result over here, that the Shannon code achieves an expected length between h of x and h of x plus 1, we can say that the Huffman code achieves an expected length which is between h of x and h of x plus 1 bits. Right? And this is the best that we can say, but note that what I'm saying over here is more stronger. Although we can say that the expected length is between h of x and h of x plus 1, the Shannon code so also achieves the same bounds, but the expected length for the Huffman code, it can be even less than that of the Shannon code. Okay, and in today's class, we'll actually prove the statement that the Huffman code achieves L star of Px. So before we proceed, any questions? Any questions? Okay, so here's a question before we proceed. Now, as we've seen, the best bounds that we have for the expected length that we have is h of x and h of x plus 1, right? Both for the Shannon code and the Huffman code. Can you give an example of a source? So we've seen that if the source is dyadic, then the Shannon code achieves an expected length equal to h of x. The Huffman code also achieves an expected length of h of x. Oh, can you give me an example of a source? Yeah, even a simple example will do, where the expected length of the Huffman code or even the Shannon code, the expected length is close to h of x plus 1. Okay, it doesn't have to be exactly h of x plus 1, even something close to h of x plus 1 will do. Can you give an example? So I'll maybe give a minute. You can think about any example. Yeah, so Shrikar has an example, very good. Uh, so if we take, so exactly as you observed, so we can achieve an expected length of h of x when the source is dyadic, or so the closer the source is to being dyadic, the closer you are to the optimal rate of entropy, right? But so if it has to be the other extreme, the worst case, so it will be farthest away from entropy when it is really far away from being dyadic. And in this particular example, if you just have two symbols, x equal to either 0 or 1, with px of 0 being, say, 0.99999 and px of 1 being 0.0001. So when it is highly biased, uh, the expected length that you can achieve, so the entropy is almost close to 0, right? So h of x is close to 0, but still you need two code words, right? You need 0 and 1. uh, so the expected length is 1 bit, sorry, yeah, so the expected length is 1 bit, whereas the entropy is close to being 0 bits. Right? And in this case, the expected length is close to being h of x plus 1 bits. And note that this is true for any code, right? So it's not, so for this example, the minimum expected length that you can possibly achieve is 1 bit. You can't go below that. So and this is irrespective of whether you're using a Huffman code or a Shannon code or a Shannon-Fano alias code or any code that you can think of. The minimum expected length that you can achieve is 1 bit, because you need at least 1 bit assigned to each code word. But on the other hand, the entropy is close to 0 bits. Right? So, so the best possible code can get you only h of x plus 1, roughly h of x plus 1 bits. Okay, so any questions? Okay, so now that we've seen that the best you can hope for is between h of x and h of x plus 1, uh, let us see why the Huffman code is optimal. Okay, so before I get to that, I'll define something called a canonical code. So a canonical prefix-free code. So a canonical prefix-free code is a prefix-free code which satisfies these three properties. Right? So note that for a prefix-free code, we're not talking about anything about the expected length, that it achieves minimum expected length or anything of that sort. It's just a variable length, uh, zero error code, which is prefix-free. Right? So prefix-free code is said to be canonical if it satisfies the following three properties. So firstly, if for symbols of larger probability, it always assigns smaller code word length. Right? So if you have two symbols, x and x prime, such that p of x is greater than p of x prime, then the code assigns a smaller code word length for x than x prime, or smaller or equal to than that of x prime. Right? And this is what you would want in a good prefix-free code. Okay, but in addition to this, we have the for two other properties. So the two longest code words, if you write down the code words in increasing order of code word length, then the two longest code words will always have the same code word length. Okay, so that's the second property. And the third property is that the two longest code words, which of course have the same length, differ only in the last bit. So all the first, so if the code two longest code words have length m, then the first m minus 1 bits are the same, and the mth bit is 0 for one of the code words and 1 for the other code word. And this corresponds to, and these two code words correspond to the least likely symbols. Okay, so let's look at an example of a Huffman code. Right, let's take maybe one example that we looked at before. Okay, something simple. Yeah, sure. So let's look at this particular example where we had 5 symbols, and the code words were 1 1 for A, 1 0 0 for B, 1 0 1 0 for C, 1 0 1 1 for D, and just 0 for E. Right? So this was a Huffman code. Now, is this code canonical? So remember that for a canonical code, we want that p of x greater than p of x prime implies that k of x is less than or equal to k of x prime. Secondly, two longest code words have same length. and two longest code words differ only in the last bit, and they correspond to the least likely symbols. Right? So if you think about the Huffman code, is the Huffman code canonical? Yes. So, well, definitely in this case, the Huffman code is canonical. But can you show that in general the Huffman code is canonical? Can you argue that Huffman code is always canonical for any distribution? So let us look at them like step by step. Okay. So it's prefix-free code. Do Huffman codes satisfy property 1?
Yes, sir. As we are clubbing the least possible probabilities at first and going to the highest possible and then assigning the codes, like in the process.
Correct, correct. So you're always starting with the least probability symbols and then merging them one at a time. So, so obviously the one with a lower probability would be merged before, or it can't be merged after something which has a higher probability. So it will get a smaller code, it will get a larger code word length than something with, it can only get a larger code word length than something with a higher probability. So it satisfies property 1. What about property 2? Do the two longest code words have the same code word length? Yes. So since we are merging the two symbols with the least probability first, right? And so those two, the ones which you merge first, will indeed be the symbols which will have the two longest code words, right? And by construction, these two code words will differ only in the last bit, right? Because the rest of the first few bits of the code words corresponding to the least likely symbols will be the same, and they differ only in the last bit. So both 2 and 3 are also satisfied for Huffman codes, right? So indeed, Huffman codes are canonical. Now I'm not yet shown that this is optimal, but by this definition of something being canonical, a Huffman code is indeed canonical. Now, what about let's say Shannon-Fano-Elias code? Is Shannon-Fano-Elias code canonical? Let's take have an example over here. Okay, yeah. So is the Shannon-Fano-Elias code canonical? So it of course satisfies property 1 and 2, but clearly it doesn't satisfy. In this particular example, it satisfies property 1 and 2, but in general it need not even satisfy property 2, and the certainly property 3 need not be satisfied. So the two longest code words need not could differ in the first few bits as well, right? So can you give an example of a probability distribution for which the Shannon-Fano-Elias code does not satisfy property 2? So give me an example where, let's see, where do I have it? Yeah. So give me an example where the Shannon-Fano-Elias code does not satisfy property 2. Right. So many examples. So Sai has an example 0.49, 0.5, 0.49, 0.01. That's a good example. And then Ritvik has another example. I guess you meant 0.99999 and 0.00001. So certainly the code word with 0.99999 would be very small, but 0.000001 would have a very long code word. Right? So both these examples uh, don't satisfy property 2. So certainly the Shannon-Fano alias code is not canonical. Okay, so Anu asked the following question: what is the difference between canonical and optimal? So a canonical code is something which satisfies these three properties, whereas an optimal code is one which minimizes the expected length. Okay, so you can have a canonical code which is not optimal, and you can also have an optimal code which is not canonical. So an optimal code will minimize the expected length, so it achieves L star of Px, whereas a canonical code is a prefix-free code which satisfies these three properties. Right? So, so we'll see how these two are different. Now, certainly, a canonical code need not be optimal because I can always sort of choose a canonical code in a rather dumb manner. So for example, so it has to be a prefix-free code which satisfies these three properties, right? So let's say, for example, I have 4 symbols, all occurring with probability 1/4. Okay, 1/4, 1/4, and let us say that okay, so let's see. Okay, so let's say that I assign 0 0 0 0 0 0 0 1 0 0 1 0 and 0 0 1 1. Okay, these are 4 code words assigned to these 4 symbols, right? Is it prefix free? Yes, it is, right? And is it canonical? So is this code that I've written down canonical? Does it satisfy property 1? It does. Does it satisfy property 2? It does, because all code words have the same length. And in fact, 2 of the longest code words differ only in the last bit, right? So these 2 code words differ only in the last bit, and these 2 code words differ only in the last bit. So it satisfies all 3 properties. It is canonical, but it is not optimal, right? Because certainly this code has a smaller expected length, right? So this is an example of a canonical code which is not optimal. And it's indeed possible to construct an optimal code which is not canonical, right? But so canonical does not imply optimal, and the either way around. But the following is always true. So suppose that we are given an optimal code. Right? So basically it achieves L star of Px. So it achieves the minimum possible expected length among all prefix-free codes. Then we can construct another optimal code, possibly different, but which is also canonical. Right? So firstly, note that uh, so both canonical and optimal codes are not unique, right? So there could be 2 different codes for the same probability distribution, and which achieves the same expected length, which achieves the minimum expected length of L star of Px, right? So there can be multiple optimal codes for a given distribution, and my claim now is that there is always at least one canonical code which is also optimal. Okay, so given any optimal code, I can transform it so that uh, it is also canonical. Okay, so is the statement clear, or are there any questions? Okay, so the way to show this is by looking at the code word tree. So always, whenever I think of prefix-free codes, it's good to think about the code tree. Right? So let's say I have some code tree like this. Okay. Now let us see. So let us look at let us look at the three properties one by one. Now suppose that we have an optimal code which does not satisfy property one. Okay. I claim that this is impossible. So if a code is optimal, then it must necessarily satisfy property one. Can you tell me why? So if a code achieves minimum expected length, then property one must always be satisfied. So, so Kusumapriya, you're close, but you need to argue in a slightly different way. Exactly. So if not, so suppose that we have an optimal code, so or we have any code for which property one is not satisfied, right? So now if I interchange the code words, so if I have an x and an x prime, such that p of x is greater than p of x prime, and k of x is strictly greater than k of x prime. Okay, so let us say that there exist symbols x and x prime, such that p of x is greater than p of x prime, and k of x is greater than k of x prime. So the expected length would be summation p of whatever p of k of a not equal to x or x prime, plus p of x k of x plus p of x prime k of x prime, right? So I'm just writing the expected length in this manner, right? So now if I interchange the code words for x and x prime, then I basically get k of x prime and k of x, right? And this, and obviously this is less than, so p of x k of x plus p of x prime k of x prime is strictly less than p of x prime k of x plus p of x k of x prime. Right? So if you interchange the code words, then you'll get another code which is also prefix free but has an even lower expected length. Right? So it can't be optimal. So if a code is to be optimal, then property one must always be satisfied. Okay?
Sir, hello, sir.
Yes.
So as earlier you said that we will have this canonical and this optimal codes are not
Correct.
unique. So actually means among all possible combinations of canonical, we will have at least one canonical which is optimal also. So isn't
Correct.
the case that this optimal code has to satisfy all the properties of the canonical code in
No,
addition to minimizing the this expected length?
not necessarily. So you can have an optimal code which is not canonical. So after showing this, I'll just come back to that point. Okay, I'll give an example of a code which is not canonical, uh, but is optimal. Okay.
Okay, sir.
Okay. So all right. So do all canonical codes have to satisfy property 2? Or do all optimal codes have to satisfy property 2? So think of this in terms of the code word tree. Okay. So you have a code word tree, and two of the code words have different lengths. So the two longest code words have different lengths. Okay. Is that possible? Okay, so the claim is it is possible. Can you give an example? Correct. So in fact, it is not possible. So let us think about why that's not possible. Right? Okay. So think about it in terms of the code word tree. Right? So you have a number of levels, and at level L max, so the maximum level, which corresponds to the longest code word length, there is only one possible symbol. Okay. So the code word tree would look something like this. Right? So in this example, this is what it would look like. So this is an example of a code word tree where the the two longest code words have different lengths. There is one code word which has a larger length, and all the other code words have length less than this. Correct? Then what can I do? I can always reduce the length of the longest code word, and it will still be a valid prefix free code. Right? So I can just erase the last bit to get this particular tree, and this is also a prefix free code, right? So if if property 2 is not satisfied, then you can take the longest code word and remove the last bit. It will still be a prefix free code, and it will obviously have an expected length which is smaller than the original prefix free code, right? So I can delete this particular symbol, and I can get a code with a smaller expected length. Therefore, an optimal code must necessarily satisfy property 2. Right? Uh, any questions? Okay, so any optimal code must always satisfy properties 1 and 2 that we've seen. Now, what about property 3? Now, I claim that for an optimal code need not necessarily satisfy property 3. Okay, so two of the longest code words need to differ only in the last bit. So, of course, the two longest code words must correspond to the least likely symbols. So, this must happen if the code is optimal. But the two longest code words need not differ only in the last bit. Okay, but you can always achieve this by exchanging code words, right? You can always exchange two different code words and or exchange bits and get a prefix-free code with the same length. So let's maybe let me see if I can come up with an example. Okay, so let's see. All right. So what can happen is the following. Sorry. So note that the two longest code words corresponding to the least likely symbols should differ only in the last bit. So what can happen is the following. Let us say that I have four probabilities. Let's say 0.24, 0.26, 0.24, and 0.26. Okay, so we have A, B, C, D. So in this, the symbols corresponding to the least probability are A and C. Right. Now let me construct a prefix-free code. Okay, so if you actually try to construct the Huffman code, then this is the code that you will get. Okay, so you can verify this later. But it's easy to see why that is true, because it's close to being 1/4, 1/4, 1/4, 1/4. Right? So if I have the following code A, B, C, and D. Okay, so this is optimal. Okay, for this distribution, this code is certainly optimal. But it does not satisfy the property. It does not satisfy property 3, because A and C, so the least probabilities symbols, the symbols with the least probabilities, A and C, they of course have the same length, but they don't differ only in the last bit, right? So A has code word 00, whereas C has code word 10. They don't differ only in the last bit. But I can always convert this to a canonical code by just exchanging the code words of B and C. Right? I can always construct the following code. Right? So note that this is not the Huffman code for the given distribution. It's a different code, but it is still optimal in the sense that it achieves the minimum expected length. But the two symbols with the least probability, The code words corresponding to those two symbols don't differ only in the last bit, they differ in some other bit. All right, but I can always exchange the code words and then get another code with such that the two longest code words or the symbols with the least probability differ only in the last code word bit. Okay, so this is optimal but not canonical. Right? Any questions? Okay, so what we've shown is that not all optimal codes satisfy property 3, but we can always find a canonical code which is also optimal. Okay, we can rearrange the code words to get an optimal canonical code. So now let us try to prove that the Huffman code or Huffman codes are optimal. Okay. So to prove this, so the proof will basically be via induction. So it will be induction on the alphabet size. Okay. So certainly if the alphabet is binary, so if there are only two symbols, then obviously the Huffman code is optimal because the Huffman code would assign bit 0 to one of the symbols and bit 1 to one of the symbols, and you can't do any better than that. Okay, so if size of x equal to 2, then the Huffman code is indeed optimal. Now, suppose that the statement is true for the alphabet size equal to m minus 1. Okay, so among all possible distributions on m minus 1 symbols, the expected length of a Huffman code is equal to the minimum expected length over all possible codes. Okay, so suppose that for size of x equal to m minus 1. Okay, so certainly it's true for m minus 1 equal to 2, right? So we'll prove this for general m. So now let's try to prove the induction step. Okay, so to prove the induction step, so consider any PMF on M symbols. Let's call it P. So this is P1, P2 up to Pm. Okay, so these are the probabilities corresponding to the M symbols. Okay, P1, P2, P3 up to Pm. Now, without loss of generality, let me assume that P1 is greater than or equal to P2, which is greater than or equal to P3, and so on. So it's an ordered PMF. Okay, so this is the case. All right. So now if I merge the last two symbols, I get another probability distribution, which I call P prime. So P prime is the PMF P1, P2 up to Pm minus 2, and the m minus 1th symbol has probability Pm, or let me call it P prime 1, P prime 2, P prime m minus 2, and P prime m minus 1, where P prime m minus 1 is equal to Pm minus 1 plus Pm. So basically I merged the two symbols with the least probability. Okay, but P prime m minus 2 is equal to Pm minus 2, P prime 1 is equal to P1, and so on. Okay, so these are two different PMFs. P is a PMF on M symbols. P prime is a PMF on M minus 1 symbols. And P prime is obtained by merging the last two symbols of P, or the two least probability symbols of P. Okay. Now let's look at L star of P and L star of P prime. Okay. Let LH of P prime and LH of P be the expected length achieved by the Huffman code. Okay, so these two are for Huffman code. Okay, so what do we know now? We know that LH of P prime is equal to L star of P prime. Right? That's just by the assumption that we made in the induction step. Okay, now what we want to show that L star of P, LH of P is equal to L star of P. That is what we want to show using this. Okay. So let us first start with L star of P. Okay. So start with L star of P. This is something, so this is Pi K star of I going from 1 through M. Okay. Now let us say that I merge, so this corresponds to some code word tree, right? Now let me look at the two least probability symbols. Okay. I'll assume that L star of P corresponds to some canonical optimal code. Okay, it's not just optimal, it's also canonical, because there always exists an optimal canonical code. So I'll take the two code words corresponding to the two least probability symbols and merge them. Okay, so that gives me another code, right? And what is the expected length of that particular code? So I'll get another code for the distribution P prime, and this is summation I going from 1 through M minus 2 Pi Ki star plus Pm minus 1 plus Pm. I'm merging the two symbols, and they will have length K star M minus 1 minus 1, right? Because the two longest code words, two least probability symbols have the same code word length. So Km star equal to Km minus 1 star, right? And I'm merging the two symbols. So the code word length for these two symbols will decrease by 1. So this is basically equal to L star of P minus, so if I write this out separately, this is summation I going from 1 through m minus 2 of Pi Ki star plus Pm minus 1 Km minus 1 star plus Pm Km minus 1 star. Yes, Divyansh, any question? Okay. Minus Pm minus 1 minus Pm, right? But the quantity we have over here is simply L star of P, right? So this is L star of P minus Pm minus 1 minus Pm. So if I merge two symbols of the least probability in the optimal canonical code, then I get an expected length which is equal to L star of P minus Pm minus 1 minus Pm. Okay, so let's call this equation 1. Okay, so now let's look at the Huffman code. Okay, so the expected length of the Huffman code for P is something. So it's summation I going from 1 through m of Pi Ki. Okay, but we know that the Huffman code is canonical. So this is I going from 1 through m minus 2 Pi Ki plus Pm minus 1 K m minus 1 plus Pm Km, right? But Km minus 1 equal to Km because this is after all a canonical code. The Huffman code is canonical. So I equal to 1 to m minus 2 Piki plus Pm minus 1 plus Pm times Km minus 1, right? But now if I merge, so if I look at Km minus 1, can you tell me what is the relationship between Km minus 1 and Km minus 2? Or let me put it in a slightly different way. So if I merge the two symbols with the least probability, it's possible that this is what the code word tree looks like. I take two symbols with the least probability, I merge them. Okay, so I'll get another code m minus 1 Piki plus Pm minus 1 plus Pm Km minus 1 minus 1 plus Pm minus 1 plus Pm. Okay, so if I merge the two symbols with the least probability, then I get another code, right, which has an expected length of equal to this. And this is precisely the expected length of the Huffman code on m minus 1 symbols, right? So that is why that is how you're constructing the Huffman code. You first merge the two least likely symbols and then construct the Huffman code for the resulting probability distribution on m minus 1 symbols. So this is LH of f p prime plus Pm minus 1 plus Pm. So LH of P is equal to LH of P prime plus Pm minus 1 plus Pm. Let me call this equation 2. Now what was equation 1? Equation 1 said that L of, what did I have over here? So L of P prime equal to L star of P. So L of P prime equal to L star of P minus Pm minus 1 minus Pm. Correct? So this was our equation 1. Now what happens if I add equation 1 and 2? I get LH of P plus L of P prime is equal to LH of P prime plus L star of P. Okay. But what I know is that LH of P prime equal to L star of P prime. Okay. Because the Huffman code is optimal for m minus 1 symbols. So LH of P plus L of P prime is equal to this. So LH of P minus L star of P is equal to L star of P prime minus L of P prime. I've just rearranged things. Okay. Now, if you look at the right hand side, this is the optimal expected length, and this is the expected length using some code, some other code, right? So this quantity, the right hand side is always less than or equal to 0, right? But this means that the left hand side should also be less than or equal to 0, right? Because L star of P prime is less than or equal to L of P prime. So this implies that LH of P is less than or equal to L star of P. But since L star of P is the minimum expected length, this must imply that the expected length for Huffman code is always equal to the optimal or the minimum expected length. Okay. Okay, Ritik, so how do we know that the probability which are same in F and, sorry, what is F and F prime? You mean P and P prime?
So the two probability distributions, the one that we considered originally and one after one merging. How do we know that in those the probabilities which are same? So P1 to Pm minus 2
Correct.
will have the same depth in the two Huffman trees. Will have the same depth. So Ki will be equal to Ki dash for I is equal to 1 to m minus 2. How do we know that?
Okay. So if you take a Huffman code, right? Take a Huffman code, and then you take any Huffman code, and then you just merge these two. Okay, so you get another Huffman code, which is something like this, right? So if you merge the Huffman code and you look at the code, the resulting code for m minus 1 symbols, then this will also be a Huffman code, right? It will be the Huffman code for the the alphabet on m-1 symbols, right?
Yes, sir.
So at every step, when you're constructing a Huffman code, you merge the two least likely symbols, and then so basically you get m-1 symbols, and then construct the Huffman code for m-1 symbols. And at every step, you are basically merging two symbols. It's a recursive construction, right? So there could be different Huffman codes, but no matter whether these are different Huffman codes, when you merge these two symbols, the resulting code tree will always be another Huffman code on m-1 symbols.
Yes, sir. Okay. Thank you.
Any other questions? So when we go through this proof once again, this is in chapter 5 of Cover and Thomas. Right? So basically all I'm covering is in chapter 5 of Cover and Thomas. I think the section is 5.8 or something. 5.8, optimality of Huffman codes. Sure, I'll also upload these notes. Any other questions? Okay, so if not, then I will end the class for today.
Sir,
Yes.
if we have
Yes, Shrikar.
if we have three symbols in our files A, B, C,
Yes.
so the probability should be 1/3 and 1/3 and 1/3.
Okay.
If we encode them using Huffman, we'll get A as 0, B as 1, 0, and C as 1, 1, right?
Sure. Yes.
So if we try to save them in a file, I mean, the original file has 3 bytes.
The original file has 3 symbols.
3 symbols, whose size will be 3 bytes. I mean, if we save them in a text file,
Sure.
the size
Yeah.
is 3 bytes, right?
Sure. Yes.
So the encoded file has only 5 bits.
Correct.
So there should be at least 8 bits in order to save the file, right? We can't save the file as 2.3 bytes and 2 bytes. It should be an integral multiple of bytes, which is integral multiple of 8 bits, right?
Yes.
So how do we save the file?
Uh-huh.
If I try to add zeros at the end and
Okay.
make it as a multiple of length of 8,
Uh-huh. Yeah.
reconstructing will be having an error, right?
Sure. So yeah. So these are tricks that you can play. So basically, okay. So if you think about it, no matter what the size of the file is, you'll have an issue with maybe the last few bits, right? So there's a difference of at most 8 bits. Sorry, at most 7 bits, right? You may
Yes.
need to sort of pad some zeros in the end. Okay.
Yes.
So the extra number of bits that you need to pad can be stored as a header,
Okay.
right, in the compressed file. So typically any compression algorithm will have a lot of header information, the PMF, and maybe some of these small things that you need to make, like additional 0 bits that you need to pad, or some modification that you need to do for such implementations. So all of these can be stored in the header bits. So when the decompressor is trying to extract the original file, it reads the header bits. It knows that the last 8 bits, last maybe 7 bits or 6 bits need to be thrown away, and then it just reconstructs using the remaining bits.
Okay, sir. Okay, thank you.
Right? So that's one implementation. It's not necessarily the only implementation that is used, but that's one way to solve this problem.
Okay, sir.
Sir, is it compulsory that we assign 8 bits for a particular code word? Like I was thinking, in case of header, I will specify the length of
Uh,
each code word.
Sure. I mean, so okay. So it's really an implementation issue because,
Yes.
so for example, no matter, so when you want to store something in memory, like in a typical computer, you can't store 2 bits, right? You have to store a minimum of 1 byte.
Yes, sir. In the 1 byte, the half bits can be the length. Like while decoding, can't we consider it?
Yeah, sure. So you'll need to store this as a header in some way, right? But but let us suppose that you have only one symbol to encode, and the code word is say 100. Okay, then you can't simply store. Okay, there's some header information anyway. Let's take care of that separately. But you can't just store 100 in memory. You need to store a minimum of 1 byte in memory, right? So you need to pad a few more bits, zeros or ones or whatever garbage bits, to make it at least 1 byte, or to make it a multiple of 1 byte, right? Say k bytes, and then store it.
Yes, sir.
That's the only thing. And this, yeah, this there you, one way to do it is you add a few number of bits. You just indicate how many bits you have added in the header.
Okay.
So that's one way to implement it.
Thank you, sir.
So,
Yes, Ritik.
so for the assignment, is it necessary to make a standalone file which has all the information, like which has the code as well the coding scheme, rather than just
No, you just need to print the
the code?
string. That's it. You just need to print a string of zeros and ones.
Okay, okay, sir. So we
You
don't
don't
need.
have to store the header or anything of that sort.
Okay, okay. Yes, sir.
Yeah, I don't care about the size of the file. Of course, if you can implement it, great. But that's not what I'm expecting. It's enough to just print a string of zeros and ones. The length of that string is what I'm looking for.
Okay, sir. Thank you.
Sir,
Yes, sir.
uh, in the same question, that padding the bits in order to make the multiple of 8.
Uh-huh.
So we need to pad 8 minus whatever the length of the uh, codes we are having.
Yes.
And at the same time, while for the decompression, we need to remove that padded bits. Is it the
Correct.
case?
Yes.
And since decompression works bit by reading,
Correct.
like you said in class also that
Mm-hmm.
1, 2, 3 like that. So we need to remove at the starting only, right, sir?
Correct. Yes. So first the decompressor will first read the header, and then from the header it will know that okay, you have to remove the last say 4 bits. It will remove the last 4 bits, so it will get a string of zeros and ones, and then it will start decompression.
Okay, sir, got it.